Alright, this is my constant velocity lab report. It's not recording for some reason. Purpose/preview: study and observe constant velocity through a real-world lens and observe the similarities and differences to experimental and theoretical models. So in this case, our experimental model will be the tracker of the marker rolling on the whiteboard, and glow scope will be computational, that's theoretical, as that is just code, and it is online and it is completely theoretical. And in constant velocity is constant speed and direction. And what to expect is we're looking at an object's constant velocity in one dimension. Okay. So Newton's first law: an object will remain at rest or at constant velocity until an external force is applied. The tendency to resist change in motion is called inertia. So the second law, is the momentum principle. Force is directly proportional to rate of change of momentum. So F net equals ma. And then in this, sorry, I'm very sick right now. In this lab, we are also using the position update formula, which is RF equals RI plus average velocity times delta t, and the velocity update formula. Okay, and in this lab, we will capture a video of the object in motion at constant speed, import the video into tracker so we can track the position of the ball on a frame to frame, and then use GlowScript to actually use a theoretical or a computational model, and then plot the data both experimentally and computationally to compare how it looks. So this is my tracker analysis. Don't have it open just yet.
There we go.
So as you can see it is constant velocity. And this is my graph, which displays the time, the x coordinate, which we don't really care about the y coordinate because it should stay the same. We're not really moving anywhere. In terms of height, we're moving in one dimension. Yeah, this is x final minus x initial over time final minus time initial, and it comes out to 0.33 meters per second. Okay, my computational model is I used the velocity that was given to me by this equation, and I used the position, and I was able to use this code to figure out the graph. And when ran, it gives me, and it highlights the initial condition, 1 second runtime, and the graph gives me this. So as you can see, it's very, very similar. Constant velocity is shown through linear form, and it assumes that the computation assumes that the net force is 0, but the experiment experiencing net force is friction and human error as well. And what if the axes were switched? It would show a very similar graph, just a different slope of the line. And is it possible to show how many pushes and pulls being added together to give 0 net force?